So you should know how to write an equilibrium constant expression. And now we are going to put the math in those formulas and solve for K. And again, it could be a KEQ or a KC. Really, again, the KEQ is just general. A KC means molarity. So you can always use a KEQ, but a KC is very, very specific. So let's write this one is asking for a KEQ, which is fine. So NO2 in brackets squared divided by N2O4. These are both gases, so you can both put them in. And then we're going to read our problem. So if it says N2O4 is 0.0045, so that goes on the bottom because my formula tells me that's where it goes. And then on the top I have 0.03, and don't forget that little square. So I end up with 0.0009. And on the bottom, I have my 0.0045. And so dividing this out, I get 0.2. And I should have 2 sig figs, so I need to say 0.20. So this equilibrium constant is just a number. And what that number tells you is whether you have more products or more reactants at equilibrium. If your number is bigger than 1, then you know you have more products. If your number is less than 1, then you know you have more reactants. So we have here a KEQ, an equilibrium constant, that's less than 1. So that means at equilibrium, we should have more reactants. So it just favors that reactant side. So this slide is just saying what I said before. Bigger than 1, more products at equilibrium, less than 1, more reactants. And one thing to note that your equilibrium constant does not have units. It's just a number. So don't worry about having molarity squared at the top and molarity at the bottom. It's not going to have a unit at all. And changing the temperature will always change the value of this equilibrium constant. So if you're comparing two equilibrium constants, you need to be at the same temperature. Let's do another example. So I'm going to write my equilibrium constant expression. And it doesn't matter if it's a KEQ or a KC. Again, KEQ is more of a general term. So my product side, I have C squared times D. And at the bottom, I have my A times B squared. And these are all gases. It doesn't say, but I'm telling you, they're all gases. And let's go ahead and plug in what we know. So at equilibrium, it says that A is 3, and B is 2, and D is 1. So I'm just plugging these in where they go in the formula. And it doesn't say what C is, so I'm just going to keep it as a C. But it does tell us what our equilibrium constant is. It's a 12. So let's work the math out. I'm going to end up with 12 is equal to C squared divided by 2 squared is 4 times 3 divided by 12. So I'm going to end up with multiplying by 12 each side. I have 144 on one side and C squared on one side. So then I'm going to square root each side. C is equal to 12. So that is the concentration. So I need to put in an M for molarity. So our K doesn't have a unit, but anytime we have any of those little brackets, remember that means molarity. Okay, this is a problem from your homework. It should be question number 55 or pretty close to it. So just match it up. Your equation should say A plus B yields C plus D, and it is reversible, and they're all gases. So we are given some concentrations at the beginning, and then some concentrations at equilibrium. So whenever you write an equilibrium constant expression, you have to be at equilibrium. So if you're given concentrations at the beginning, you need to make what is called an ICE chart. So it's an initial, change, and equilibrium chart, or ICE chart. So you're going to write your balanced equation across the top. So I have A plus B yields C plus D. And I like to draw kind of a heavier line separating the products from the reactants, just so I can keep them straight. And then let's fill in what we know. So it says at the beginning, the concentration of A is 1.2 and the concentration of B is 1.2. Then it says at equilibrium, C is 0.8. So we have to put it down here at the equilibrium line, 0.8. And now it says find our equilibrium constant, our K. Well, it doesn't say what C and D are initially, so we're going to assume that we don't have any of them. So we start off with nothing. So an empty container just filled with A and B. Because we have a lot of reactants and no products, we know the direction the reaction is going to go. So equilibrium is going to be achieved by shifting to the right because I don't have any products. And remember, at equilibrium, you need to have some reactants and some products. You should have some of everything. So I know it's going to shift this way. I know that my A is going to disappear. At the same rate, my B is going to disappear. And that is because my stoichiometry is 1-to-1. Let's look at C and D. I know that every time a C appears, a D will appear. So I'm going to again put the stoichiometry in the change step. These are all ones. So the next problem will be a little bit more exciting, but this is just a real basic how to do an ice chart. I will always give you one of the equilibriums, or at least give you enough information that you can solve the problem. But this ends up being how you solve for x. So you're going to look at one column, and it's going to be a little algebra problem. 0 plus x equals 0.8 in this case. So what does x equal? X equals 0.8. So now I can solve for x. So look on the first column for A. So 1.2 minus x, which is 0.8, and I'm going to get 0.4. And then let's look at B. B is going to be the same number. And let's look at D. D, I have 0 plus x, and I know x is 0.8, so it'll be 0.8. So now I have all my concentrations at equilibrium, and I can plug it into my equilibrium constant expression. Please, please, please do not skip the writing the formula step. This is where the biggest mistakes occur with students, is they think, oh, this is easy, and they just plug the numbers in products over reactants, and they forget the stoichiometry. Now this one doesn't really have very much stoichiometry, but let's go ahead and plug it into our formula. So we have 0.8 times 0.8 divided by 0.4 divided by 0.4. And we get as our final answer 4. So what does this number mean? Because it's bigger than 1, then I know that I have more products. And it doesn't tell us to say that, but it's a good reminder of what that number means. So again, make your ice chart, write your formula across the top, and you're going to put your stoichiometry in your change step, and then do each column, solving for x. Hey, this is also another problem in your packet. It should be pretty close to question 56. If it's not, I'm sorry, just look for it. So 2E plus F yields G plus 2H. We are going to start off with, I think this time, writing our equilibrium constant expression. So I'm going to have G on top times H cubed, and I'm going to have E on the bottom squared times F. All right, let's look and see what values they give us so we can solve this. So find Kc, so the equilibrium constant. At the beginning, E is 5, F is 4, and it doesn't say what G and H are, so I'm just going to put in a 0. And then it says at equilibrium, G is 2. All right, so now let's look at the change. So this one has the stoichiometry in it. So you're going to see this in the change step. So I start off with just reactants. I'm going to make products. So I know my reactants are going to disappear and my products are going to appear. My E is going to disappear twice as fast as F. And so all I do is I take that number that's in front of the E and I put it in the change. All right, so again, E disappears twice as fast as F because of the stoichiometry. Let's look on the product side. We have H appearing 3 times as fast as the G. All right, and we can solve for x because I have one column completely filled in. So I have 0 plus x equals 2, so x equals 2. I can go and plug this in for my whole ice chart. So on the first one, I have 2 times a minus 2, which is a 4, so I just get a 1. For F, I have 4 minus 2, because again, x is 2, and I get a 2. I already know what G is because I was told. And the last one, I have a 3x. So with x being 2, this will be 6. Now I can just plug it into that formula. So this is why that formula is so important, to remind us that the h needs to be cubed and the e needs to be squared. So let's go ahead and fill it in. So we have our G is 2, our h is a 6, and our e is a 1 squared, and our f is a 2. So we can just do our math now. And I get 216. Again, no units. And will I have more products or more reactants? I should have more products.